right. Hello, everybody. I'm going to start 30 seconds early because I have the microphone and I can. So I'm gonna. My name is Laura Frank. I'm the Director of Engineering at CloudBees, formerly Codeship. We just got acquired about 3 months ago. So we're very happy to be joining up with a bunch of other people trying to solve DevOps problems. However, I'm not here to talk about CI or CD or anything like that. I'm here to talk about distributed consensus, which is a really scary thing. But I'm going to try to make it a little bit less scary for you. I'm going to go over a couple main topics today. First is demystifying this very intimidating phrase called distributed consensus. We're going to talk specifically about the Raft consensus algorithm, what it is, where you find it, why it's there. We'll talk about quorum, which is essential to understand if you're operating any system that depends on distributed consensus. We'll talk about leader election and log replication, and then just maybe at the very end, I will break a cluster because it's my favorite thing to do. So I'm not necessarily showing best practices if you're operating a cluster in production. That's not really the point of this talk. I'm here to give you a little bit more theoretical background for the sort of theoretical underpinnings of what makes the Kubernetes world go round. So let's get started first with distributed consensus. And I really like saying this term or like bringing it up at a party. I'm real fun at parties. It sounds really fancy, but what it means is just getting more than one party to agree on something, and that those parties are not all located in the same place. So we're really focusing on agreement. And the reason that we have to do that is because we've sort of made it our own problem, or we've sort of created the problem for ourselves. So we used to not really have to worry about distributed consensus because the world was really easy. We had a client that maybe made a request to a server to update a value, and the server kind of knew what the values were and said, yep, cool, I'm going to append that value, and then my new value is 7, for example. We use tools like Kubernetes, though, because we don't want that model anymore. We don't want there to be a single point of failure or just one database. We want redundancy and fault tolerance, and that means having multiple entities. And in a lot of cases, that means having a management group or consensus group that is comprised of more than one machine. So we have to get all of those machines to agree on the state before we can take an action on our cluster. So in this distributed model, here's a visualization. So we have a client making a request, but then that request needs to be decided upon by a manager group. And in a manager group, there's always a leader. That's the node that's taking in the requests. And then there are followers who are participating in that consensus group, but aren't necessarily in control of making the final decisions. So they'll get requests to say, hey, from the leader, like, hey, can this happen? Is this possible to happen? And those followers can respond, yep, thumbs up, let's do it, and then the leader can confirm it. But there's different roles, and we'll talk about those roles in a management group as the talk progresses. So the problem with clusters is that having n machines agree on a single thing, or having n anything, whether it's people or cats perhaps, agree on a single thing is really hard. And that's where Raft comes in and kind of does the heavy lifting for us. So what is Raft? This has been, I think, one of those underground parts of our system that we didn't really talk about much, but in the last couple of years, it's gotten a lot more popular and a lot more visibility, which makes me happy because I find it very interesting. Raft is an algorithm to manage consensus-based systems, such as container orchestrators. It can be certainly used in other kinds of applications or other ways as well. I would also encourage you not to get too intimidated maybe by the word algorithm in Raft, because it is a complex system, and it's just a system of patterns, and I think it can be really accessible. It just sounds a little bit intimidating, which hopefully you'll find out by the end of this talk that it's easier to understand. It's designed to be easier to understand, so if you are from a traditional CS background, you might have studied Paxos or multi-Paxos. That was a bad time in my studies, so the laughter tells me it was probably a bad time for you as well. Raft came out as like the opposite of that, like, hey, this was really painful. Why don't we figure out a way to make this not only perform as well, but also a little bit easier to understand, so that the people who are responsible for operating systems that use this algorithm can actually, understand what's going on and be able to kind of process it at a human level. It also has a cute logo, which I just found out about yesterday. I didn't know it had a logo, but there it is. I guess it's named Annie. At least that's what the PNG file was called, so I'm going to go with it, Annie the Raft. So Paxos, multi-Paxos, all of these distributed consensus algorithms are really painful. And they're very complex and have so much risk and so many edge cases, and they're dealing with lots of responsibility that no sensible person wants to write their own, except the authors of Raft, but they had good reason to. And because this is such a kind of a solved problem, algorithms or systems like Raft do have a lot of popularity because there's no reason to implement it yourself. It's like really hard to implement yourself. And for that reason, Raft is used in a lot of places. So orchestration systems, I think, are the most visible way or most visible place that Raft is used. So Kubernetes using etcd, and then by extension, every single system that uses etcd in any way, shape, or form is using Raft because Raft is embedded inside of etcd. Docker uses Raft. It's embedded inside of Docker itself. Docker doesn't have a reliance on etcd for their orchestration. Nomad has a similar approach where Raft is kind of baked in the internals. If you are familiar with Zookeeper, Zookeeper uses something slightly different from Raft called the Zookeeper Atomic Broadcast, which is ZAB, which is fun to say. It's similar to Raft, has a lot of the same responsibilities, a lot of the same patterns, just it's not Raft. But luckily, the patterns are very similar. So if you're using Zookeeper, in some way you can kind of translate what we'll talk about today onto that. Raft has 3 main responsibilities wherever it's being used. The first one, and probably the most important one, is log replication. Raft is there to maintain a consistent state across your distributed node, distributed nodes that are participating in that consensus group, and then by way of that consensus group to your entire cluster. We'll talk about each of these in more depth as kind of the main meat of the talk. Leader election is another thing. So as I said before, inside of any consensus group, there's a leader that's taking in requests and then asking basically for permission or asking the followers if that action is allowed to take place. So there has to be a leader. If that leader goes offline or is unreachable, then we have to elect another leader in order for the world to keep going around. Safety is another responsibility of Raft, and I'm not going to go into depth on this because it's sort of baked into both log replication and leader election. Safety is the sense that any action that is happening in the cluster should be allowed to happen, and Raft is designed to make actions that shouldn't be allowed to happen impossible to occur. And that's sort of baked into both log replication and leader election, so I won't go deeply into safety today, but that was one of the design goals of Raft. I think one of the other big things that Raft is responsible for is being easier to understand. As we are using tools like Kubernetes more in production and we have people responsible for operating them, if something happens with your management group or your consensus group, if you lose quorum or something goes wrong, it's not fun. And I think it's always better to be able to really understand what's going on so you can troubleshoot. And that's one of my goals also for this talk, is to give you some more fundamental knowledge. So the first thing that we'll talk about in terms of fundamental Raft knowledge is quorum. And this is a buzzword, maybe it's fun to say, I think. Quorum is not a term unique to computer science or orchestration systems or etcd or Raft or anything. This is a borrowed term. It is just the minimum number of votes needed to perform an operation. I think usually we hear this term in government, depending on what country you're from. Sometimes the groups of elected officials need quorum in order to conduct a vote. And this is the same idea. It's just a borrowed concept. Without quorum, nothing can happen because the system is not allowed to do work. And I think we have a general idea that quorum means majority. And it doesn't just apply to nodes being online. They have to actually agree and vote for the same thing in order for that action to take place. So majority is a good way to think about quorum. It's also a much easier word to understand and to spell and to pronounce. But it's I guess, slightly different. Quorum is specifically defined if n is the number of nodes in your cluster, n divided by 2 plus 1. So the most important thing about that is distinctly and precisely more than 50%. 50% does not constitute quorum. It has to be some value above 50%. And thankfully, because this is just an easy mathematical expression, we can fill out a chart. And you've probably seen a chart like this if you are operating etcd or another system with a consensus group. This is a pretty common thing to say, OK, how many nodes should I have in my consensus group in that cluster? If you have one node, in here I've labeled those Raft consensus group participants managers. That's a common term to describe them. If you have one node, obviously quorum is 1. If that node goes away, then you can't do any more work on your cluster. If you have 2 nodes, quorum is 2, because 2 divided by 2 is 1, plus 1 is 2. So it's really not getting you anything extra. But when we go to 3 or 5 or 7, we can start to see that there's a pattern that the odd numbers seem to be more efficient. One other way to think about quorum is not about how many you need to satisfy quorum, but what your fault tolerance is when you're making these choices. So if we go all the way back up to 1, our fault tolerance is obviously 0. We can't survive a failure of a node in that case. The same is true for 2. We can't survive a failure. But if we have 3 nodes in our consensus group, quorum is 2. That means 1 can go down, or maybe there's a network partition or something happens where it's unreachable, and our cluster can still be up and running and perform new work. So my recommendation is that if you're running something in production, especially if it's making money, 5 is sort of the magic number, because then you can tolerate 1 failure and then have 1 node down for maintenance. So just my experience working with many different projects in production, that seems to be sort of the magic number. Again, even numbers are not very efficient in this type of model because of that n divided by 2 plus 1 and over 50%. You don't actually get any more benefit if you have 1 manager. Just adding another isn't going to give you more fault tolerance. And in a very counterintuitive point that's always mind-blowing when I share it with people who haven't thought about it in this way, having 2 managers actually doubles your chances of losing quorum. Because you still have 0 fault tolerance, and now instead of having 1 single point of failure, you've doubled your chances of having a node failure by introducing another one. So stick to odd numbers, stay away from even numbers, and you'll be good. If you are deploying your consensus group across multiple AZs, which you might have a good reason to do so, I think deploying them across multiple regions can get a little bit hairy because of latency, and we'll talk more about like node-to-node communication in a bit and why that can be a problem, but multiple AZs might be reasonable, so just pay attention to data center topology when you do that. Anticipate that one of those AZs will go down, and that the status page won't be updated for that cloud provider. Not going to name any names. But there's it's math. It follows that same quorum principle, just anticipate failure. I think that's a really good strategy in general for distributed computing. A lot of turnkey solutions that might stand up or bootstrap a cluster for you magically kind of have this functionality in it. If you're using something like an auto-scaling group as part of that, generally we'll try to distribute evenly across the AZs to make sure that you're resistant if one of the AZs has a failure. So keep an eye out, but I would always double check to make sure that you're insulated from that, or isolated from that failure. So that's quorum. Quorum is going to become a very important thing as we talk about both leader election and log replication. So leader election is very important and one of the core responsibilities of Raft, because without a leader, your management group or your consensus group can't do any work because there's no one to delegate responsibility and control whether or not a log can be appended or should be committed into the log. In a consensus group, there are really 3 states of nodes that participate. One of them is the leader. The leader is, again, the one taking in the requests and then sending messages out to the followers, which is the other state, to make sure that that action is able to take place. And it gets confirmation from the followers, commits it, and then sends that message back to the followers to say, okay, yeah, you can really, really write that into your log now. We've gotten enough votes. There's a third state called a candidate, which happens in leader election. If the leader is unreachable or goes offline for some reason, if you execute chaos monkey scripts in your cluster, like some people might do, then your consensus group doesn't have a leader, and we need to go into leader election. The first follower to notice that there's no leader will put itself into candidate state in order to solicit votes from the rest of the nodes that are online to elect itself as the new leader. It will also vote for itself. There's also another state, which is kind of an unofficial one, which is unreachable. I think that's important to remember, that there can be nodes that are formally participating in the consensus group that could be unreachable. So that could be the downed manager or a downed node or the downed leader that's spawning the next leader election. They still exist, even if they're not online. So I want to talk through a couple scenarios of leader election. And to do that, I have a little handy visual aid. I actually forked this from, let me see if I can make this bigger. Cool. Yeah, you can all see that, okay. I forked this from the author of Raft and kind of tweaked it a little bit for this talk. If you've ever looked at The Secret Lives of Data, if you are an independently curious Raft consumer, then you may have seen something like this before. I want to talk through what happens during a leader election. We're going to start out really slow. So a couple things to pay attention to. We have a 5-node consensus group up here. Starting with S1, S2, S3, those are the names of the nodes in the consensus group. We have this little ticker that's going around, and that's a timeout. And I said before, like the first manager to notice, or the first node to notice that there's no leader is going to put itself up for election. And that's exactly what happened right here with S2. Notice that there was no leader, so it timed out and put itself up for election, solicited votes, and I can rewind time a little bit here. Oh, sorry. Oh God. I just got a new MacBook with the touch bar and like the huge trackpad, and I'm very unhappy with it. So please bear with me. There we go. Okay, so we see that S2 timed out, and now we have a new election cycle, so election term 2. We see 5 spaces for votes in there, those little circles. We can see that S2 voted for itself. It gets a black circle from itself. It's asking for votes from the rest. And everyone's online and everyone votes, and that means, yep, S2 gets elected as the leader, and we see that in red a little bit. Probably hard to see for those of you in the back. So that's great. And things will just carry on until, oh no, S2 went down. Whether or not there was a hardware failure or there's a network partition or who knows what could happen, but the point is that it went down. And just as in the last time, the first node to notice that there's no leader is going to put itself up for candidacy. Now, quorum becomes important here because we have 1 node that's down, but since we have a 5-node cluster, quorum is 3, which means that 4 is fine, and we can keep going and we can tolerate that failure. So S3 is going to notice that there's no leader. It will vote for itself, solicit votes. It's not getting any vote back from S2, but that's fine because it has already 4 votes, 1 from itself and then 1 from each of the other nodes that are online. Let's speed this up a little bit. Cool. There's one thing, actually there's many edge cases that can happen in this, and one that I find particularly interesting, and one thing that's a little bit different in Raft versus other implementations like Paxos and multi-Paxos is the event of a split vote. So this is highly unlikely because these timeouts are randomized across all of the nodes, so it's highly unlikely that 2 nodes in your group have the same timeout, but it can happen, and in this case it has. So I can go back in time just a little bit and see that these 2 nodes, S1 and S5, timed out at exactly the same time and put themselves up for candidacy for election term 4 at exactly the same time. They also sent votes out at exactly the same time, and they're voting for themselves, so they have 1 vote, but they can only manage to get 1 other vote back because it is a truly split election. Quorum is, again, how many in this situation? 3. So 2 votes isn't enough to elect a new leader. But what happens then? Because it looks like we'd be just at a standstill. Raft is designed, though, if there's no leader, whatever the next node is, which in that case was S3, to notice that there was no leader, is going to put itself up for election. And let's just go through that. So S3 right here is just about to time out. It doesn't matter the candidacy state of S1 and S5. They don't have enough votes to be elected. So what Raft does is just throws out that cycle. It just counts it as lost, and we're moving on. We're not going to try to repair it or try to do anything. We're just going to plow forward. So S3 will put itself up as a candidate for for election term 5. And since it was the only one to do that, it's going to be able to get the votes. Having a candidate state of a node doesn't prevent it from voting for another node as well. So S1 and S5 are able to participate in that election. It can get the requisite votes, so it gets 4 in this case, and time marches on. We've just moved on to a different election cycle. So that is leader election, kind of a brief intro to it. There's a couple other edge cases that are captured, but I think that split vote is really the most common that is possible to happen. The next thing that I want to go into a bit more depth on is log replication, because it's kind of similar with that heartbeat timeout transaction between the manager and the followers, but it's a little bit more complicated. So we're going to combine sort of everything we've talked about so far and talk about log replication. Before we do that, though, I want to make it clear what I'm talking about when I'm talking about a log. I think this is also one of those terms that's like highly loaded, and it needs like that Wikipedia, like which log are you talking about page when we discuss it. This is the source of truth for your application. I'm not talking about log output or system log. I'm talking about like, imagine someone hammering values into a stone tablet kind of log, a record of truth. So this is an append-only time-based record of data. We can visualize it really simply by imagining just a list of some values that, let's say, X has. So at one point in time, X had 2, and now we're going to maybe append an entry for whatever the new value of X is. This log is specifically for computers, really. It's not for humans. Luckily for you all, I am a human with a computer, so I'm going to show you how you can actually read the Raft log and where it's found, which I think is pretty interesting. Before we do that, let's look at what happens in this log replication scenario and go over a couple bad states with some data inconsistency and see how Raft repairs them. So in this case, we have 2 states for a log entry to be. One is uncommitted, and those are represented by the little dashed lines. If we see S1 has 222, those are all uncommitted. That means that the leader has said to the follower, please update this to 2, but has not gotten enough votes and enough confirmation to make that truth yet. So that's uncommitted state. That's sort of like, pre-commit, not yet in the log. So in this case, we don't have quorum, so nothing can be committed. We can have these things in an uncommitted state, just sort of like preparing it to be committed, but because we can't get enough votes, there's no way for that to become true. This will go on, and we'll just populate whatever nodes are listening with these uncommitted log entries. Let's move a little bit faster and see what happens then when we do have quorum. 1 came back, which means that we can now start committing these. So now that enough votes are possible, even though those nodes knew about the possibility for change, that change hadn't yet been voted on, so it's not been committed in the log. Now they have been, so that's represented by this solid line across or around the log entry. The one really interesting thing about Raft is what happens in the case of data inconsistency. So in this example, we had some nodes offline, but I don't know what they were doing. They could have been on a separate partition and had a new election cycle and had a new state of truth. We don't know. But now let's say that happened and maybe the network partition is restored. What happens now? We have 2 sets of data, and how do we repair the inconsistencies? And in general, the answer to that in Raft is that whatever the most recent election term was, that data gets precedence. So in this case, we've already moved on to election cycle 3. We have the old leader, which was S1, is offline now, so we have kind of like 2 conflicting sets of data. When S1 comes back online, it still thinks that it's like the year 1995, or it's like election term 2. It doesn't know what leader has been elected. It will get informed soon by the new leader, so it updates itself to understand that it's election term 3. And because it had only uncommitted logs, it can throw those out and then reconcile itself with the new version. Cool. So there's, of course, other edge cases, but I think that network partition is particularly the one that you might find in production and is more likely to happen in real life. So if you are new to logs or kind of new to log replication or distributed consensus, there's a really awesome blog post about logs and what you all should understand about them if you're going to be operating any system that depends on a log. I have it up on a handy little bit.ly. It's a LinkedIn engineering blog post, so highly recommend that. It's a kind of a long read, but a good one, so if you want to check that out. Cool, so I promised that I'm a person with a computer, or a human with a computer, which means that I'm able to look at the logs. So I actually wanted to do this live, but the Wi-Fi was choking a little bit, so instead of me kind of like fumbling and waiting for Wi-Fi to error out, I just prepared this beforehand. But I can talk through, maybe I can talk through what this is. So I'm gonna do something like scandalous, and I'm actually going to use Docker for the example for Raft instead of etcd, because I find the tooling just slightly better for conference talk demos specifically. There is so I said before, Raft is embedded directly in Docker, and everything lives in a directory. In etcd, it's living in varlib etcd member. There's a snap directory and a wall directory, so snapshots and then the write ahead log. Write append log, write ahead log. Those are in etcd. They're just file, and it's the same thing because Raft is the consistent part here, so it doesn't really matter what tool we're talking about. That's also available in Docker. And when I use this, there's a tool called Raft. There's a dump wall tool in SwarmKit, and I'll have links in the slides so you can check it out later. It's a little bit too much detail to kind of try to process during a talk. But it basically looks at that log, processes it into something that's human readable, and then spits it back out. So I have a cluster here of 3 in a Raft consensus group. And basically what's stored in the Raft logs is everything that you could possibly need to know about the state of the cluster. So we have the action that happened, we know the index, we know exactly when it was created, when it was updated. We can see the image, we can see resource limits, status, kind of everything is here. Which is really great because if you have this Raft log, you can basically breathe life into your cluster in case of a failure. And there's a couple different failure scenarios that I want to talk about, and we'll talk about this Raft log and its role in each of those. The first one is the hard failure of like your data center being on fire. So this is like worst case scenario, but I want to emphasize that you should be backing up these logs that are controlled by Raft. As long as you have that log, you can restore the state of your cluster. You know, like asterisk, there's probably some little things that you're not going to be able to restore, and you can't restore what happened after you took the backup. But you can kind of rewind time and breathe life back into a failed cluster if you've sort of declared bankruptcy in your incident response and need to start from scratch. As long as you have that backup, you can do it. Generally speaking, wherever Raft is implemented, there's going to be 2 directories. There will be a snapshot directory and that log directory in wall. In etcd, you can specify where these come from or where they're stored, so you can put them somewhere else. You can back them up somewhere else. You can kind of define a disk and a dir of your choice in etcd at least, so that's a really cool feature. Some tools will manage this for you. I think that's becoming like the new horizon of Kubernetes management, is just to automatically back up etcd so that you always have something on hand. If your cluster goes down in a dumpster fire, you can just sort of bring it back up. If you're going to restore from a backup, so in etcd, you want to pass in where those things come from. So where that data is coming from, where the wall is coming from. And then there's this really important thing called -- force new cluster. And this seems to be the agreed upon flag for kind of all tools that are dealing with distributed consensus. That will force a 1-node cluster to kind of come online with the data that is in that backup. You can do this the same thing on Docker, again, because it's not anything specific to the tooling. It's about Raft and about that Raft log. Same thing, Docker swarm init with that -- force new cluster will kind of disregard the cluster configuration you had before, take that log, and start a brand new cluster with 1 node using that backup. One important thing to keep in mind, and I'm hoping that this will be a solved problem in maybe a couple of months' time. I know there's a lot of smart people working on this problem. When you restore from the backup, those like member IPs of the nodes that are in the cluster are also stored as part of that log, which means that if you have a brand new cluster, the IP addresses are probably not going to be the same. In etcd, what's really awesome and probably one of my favorite features that's very underappreciated is that it's super easy to update a member IP. You can just like go in there and say, oh, I have a new node that's replacing this old node. This is the new IP address. Swarm, at least the last I checked, maybe it's different. You can't really do that in a graceful way. I think that's one really great thing that etcd has for it. If you're an SRE or someone that's on call, that's something that makes me sleep a little bit better at night. So let's talk about a soft failure, and I'll demo a soft failure because that's hopefully, fingers crossed, one I can recover from more easily and with the time allotted so that I can get you all to lunch on time. So losing quorum is probably the most common failure. It's not common that our data centers like go up in smoke. So you probably want to practice that backup recovery, every month or every week or whatever your policies are. Practice also what happens when you lose quorum, because it can mean different things for your application. So losing quorum just means that no new action can take place. It doesn't mean that everything that's running falls down. All right, and that's an important distinction. So understand what that means for your app. If you have just a bunch of services that are long running and you're just using a tool like Kubernetes because you want fault tolerance and resistance to failure, then that's maybe okay and not such an emergency, because unless there's a failure, everything's just going to stay up and running. But if you're using, if you're processing tons and tons of jobs, those new jobs aren't going to be able to be run. The interesting thing about losing quorum is that you also can't add new nodes to that management group. So let's say you have 3 nodes, you can't just, and 2 of them go down, you can't just start a new node and add it to the group and try to force quorum to be regained, because your management group can't agree that it's possible for a new manager to be added. So how do you survive a quorum, losing quorum? You can regain quorum by bringing the down nodes back up. That's kind of Captain Obvious, probably not something useful in a talk. But it is there, and I think it's maybe you don't think about that in incident response. The other thing you can do is that this is sort of like that disaster recovery that we talked about before, but you can use force new cluster on a healthy manager that's part of the management group or the consensus group, and do -- new force new cluster, and that will just look at the current Raft log that it already has. There's no need to restore from backup, and just disregard the fact that there were at one point other managers. You will have to re-add new nodes to that leader group if you do it this way. And again, you can't just add a new healthy manager to the cluster, because that would require consensus, and that's something that we don't have. That's what I will show you right now. And I have a little visualizer here. I have 3 nodes participating in this consensus group, and I have Elasticsearch running here. So we can go down and, oops. Get rid of this. Oh, I'm in a container. Always in a container when I don't expect to be. I can curl and just look at what my Elasticsearch is doing, and we can see it's online, for search. So it's here and it's running, and that's great. I have 5 replicas right now. But let's not have consent. So I'm going to take 1 away, and this might just take a second to realize that that node is down. We can see that failure, so we can expect that that 5th one will be rescheduled soon. Cool. Everything's happening just as we expect. That's because we still have quorum and things are fine. But if this always makes me a little nervous. It's fine. It's just virtual machines. It's okay. It's I should put a warning no VMs were harmed in this. It's fine. But now I'm I did a bad thing, because now not only did I kill a node where I had work running, but now I just I lost everything because I only have 1 node that's up. But the interesting thing is, though, oh no, now I lost Wi-Fi. Oh no. Oh crap! See, I didn't anticipate that happening. Yeah, that's fine. Let's see. Oh man, PC cast. Okay. That's fine. We have 1 minute left. I'll just talk to you about what happens. So I'll give it like a hot minute, and then we can see. Oh man, I expected a lot of failures. I did not expect that one, so I was very trusting of conference Wi-Fi. So what happens in this case if we... so I killed node 2 and node 3, leaving node 1. And what I'm going to do on there is just go docker swarm init, or use the etcd command that's the equivalent, and -- force new cluster. It's going to look back to the Raft log that's stored in that wall directory that we talked about before, and just kind of revive itself, understanding that then there were supposed to be 5 Elasticsearches replicas running, and it's going to revive those 5. But we still have kind of some cleanup to do, because we didn't actually gracefully terminate the other nodes, so we have to get rid of those 2 old nodes that were in our consensus group manually, or scripting, or whatever your tool of choice is, and then re-add new managers if I want more than 1. Let me try this one more time before admitting defeat. That's fine. So I will leave. Actually, this is always up because I have a really bad habit of buying domain names. So I own consensus.group because I really love Raft. So this is up in perpetuity. You can check this out, or Secret Lives of Data. I will let you all go to lunch, but I'm happy if you want to come up to the stage after to answer any questions. So thank you so much. Sorry about the Wi-Fi.